There are some basic probability relationships that can be used to compute probabilities of events without knowledge of all sample point probabilities. The complement of event A is not being in event A. The union of two events has at least as many sample points in it as the event with the most sample points. If you are a black female student, you are in the union black students and male students because you are black or male. The intersection of two events generally has fewer elements in it than does the union of the same two events. If you are a black female student, you are not in the intersection of black students and male students because you are not black and male. Two of the biggest problems students have is understand the difference between mutually exclusive events and independent events. The union of events is computed by adding their probabilities if the events are mutually exclusive. The intersection of events is computed by multiplying their probabilities if the events are independent. A Venn diagram can be used to illustrate the complement of an event. The complement of event A is defined to be the event consisting of all sample points that are not in A. The complement of A is denoted by A superscript C. Suppose a red circle contains all the sample points in event A. All of the sample points not in A must be in the gray part of the diagram. The equation for computing the probability of A complement is 1 minus the probability of A. Let A be the event 55 years of age or older. Using the data from the World Almanac 2004, compute the probability of complement A. The red box identifies the sample points in event A and their probabilities. The probability of A is the sum of its sample points probabilities 0.09 and 0.12, which is 0.21. The gray box identifies the sample points not in A and their probabilities. The probability of A complement can be computed directly by summing up the 5 sample point probabilities in the gray box, which is 0.79. Using the equation for the complement, the probability of event A's complement is 1 minus the probability of event A, which is 1 minus 0.21 or 0.79. A Venn diagram can be used to illustrate the intersection of two events. The intersection of events A and B is the event consisting of all sample points that are in A and B. The intersection of A and B is denoted by A intersect B. Suppose the circle on the left contains all of the sample points in event A, while the circle on the right contains all the sample points in B. All the sample points that are in A and B are in the red overlap area called the intersection. Since events A and B intersect, the probability of their intersection, the probability of A and B, is not equal to 0. When this occurs, we say A and B are not mutually exclusive. Let A be the event 55 years of age or older. Let B be the event 64 years of age or younger. Compute the probability of A and B. The blue box identifies the sample points in event A and the probabilities of the sample points. The probability of A is the sum of its sample points, which is 0.21. The pinkish box identifies the sample points in event B and the sample points probabilities. The probability of B is the sum of its sample points probabilities, which is 0.88. The darkest box is the overlap of the two events. This box identifies a sample point that is in the intersection of A and B. The probability of A and B is 0.09, which is why we have this in red and that in red. A Venn diagram can be used to illustrate the intersection of two mutually exclusive events. The intersection of events A and C is the event consisting of all sample points that are in A and all sample points in C. The intersection of A and C is denoted A intersect C. If the circle on the left contains all of the sample points in event A, and the one on the right contains all of the sample points in C, then these two circles do not overlap, which means that none of the sample points that are in A are in C. Hence, the intersection is empty. When events A and C do not intersect, the probability of their intersection, probability of A and C, is equal to 0. When this occurs, we say A and C are mutually exclusive. Let A be the event 55 years of age or older. Let C be the event 24 years of age or younger. Compute the probability of A and C. The blue box identifies the sample points in event A and their probabilities. The probability of A is the sum of its sample points probabilities, which is 0.21. The pinkish box identifies the sample points in C and their probabilities. The probability of C is the sum of its sample points probabilities, which is 0.36. Since the two boxes do not overlap, they do not share sample points. This means there are no sample points in the intersection of A and C. Thus, the probability of A and C equals 0. And A and C are called mutually exclusive events. A Venn diagram can be used to illustrate the union of two events. The union of events A and B is the event consisting of all sample points that are in A or in B. The union of events A and B is denoted by A union B. Suppose the circle on the left contains all of the sample points in event A, while the circle on the right contains all the sample points in event B. All the sample points that are in A or B are in the union of these events. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of their intersection, which is not 0 because A and B overlap. This is the addition law for non-mutually exclusive events. Let A be the event 55 years of age or older. Let B be the event 64 years of age or younger. Compute the probability of A or B. The blue box identifies the sample points in event A and their probabilities. The probability of A is the sum of its sample points probabilities, which is 0.21. The pinkish box identifies the sample points in event B and their probabilities. The probability of B is the sum of its sample point probabilities, which is 0.88. If we simply add these two probabilities together, the result is larger than 1. Probabilities cannot be larger than 1. It's larger than 1 because the intersection probability is 0.09. It was counted twice. It was counted once here and once here. Thus, when the intersection probability is not 0, we must use the addition law for non-mutually exclusive events, which is the probability of A plus the probability of B minus the intersection probability. The probability of A union B equals 0.21 plus 0.88 minus 0.09, which is equal to 1. This makes sense because everybody is either 55 years of age or older or 64 years of age or younger. A Venn diagram can be used to illustrate the union of two mutually exclusive events. The union of events A and C is the event consisting of all points that are in A or C. The intersection of A and C is denoted A union C. Suppose the circle on the left contains all of the sample points in event A, and the circle on the right contains all of the sample points in event C. Notice that these circles do not overlap. This means that none of the sample points that are in A are in C. Hence, their union includes all events in both with none of the events being counted twice because there's an intersection, because the intersection is empty. The probability of A or C is equal to the probability of A plus the probability of C minus the probability of A and C, which is 0 because A and C do not intersect. Thus, the probability of A or C simply equals the probability of A plus the probability of C because the two events are mutually exclusive. This is the addition law for mutually exclusive events. Let A be the event 55 years of age or older. Let C be the event 24 years of age or younger. Compute the probability of A or C. The blue box identifies the sample points in A and their probabilities. The probability of A is the sum of its sample point probabilities, which is 0.21. The pinkish box identifies the sample points in C and their probabilities. The probability of C is the sum of its sample point probabilities, which is 0.36. To compute the probability of A or C, we simply add their probabilities because the intersection of A and C contains no sample points, meaning the probability of A or C is equal to 0.57. The probability of an event given that another event has occurred is called a conditional probability. Conditional probability was introduced in Chapter 2 when we constructed cross-tabulation tables and discussed Simpson's paradox. The conditional probability of A given B is denoted by the probability of A given B. The vertical line between A and B means given. The use of the symbol is similar to the U-shaped symbol in the probability of A union B, or the upside-down U-shaped symbol in the probability of A intersect B. The U-shaped symbol means or, while the upside-down U-shape means and. The conditional probability is computed as follows. Probability of A given B equals the probability of A and B divided by the probability of B. B. Given B means we're dividing by the probability of B. B follows a vertical line, which means given, while the probability of B is in the denominator of the fraction. The hypothetical example below shows how many black and white workers are hired or not at Big Mart. There are 130 white workers and 30 black workers, but 570 white workers and 250 black workers were not hired. 700 white workers applied for work at Big Mart. 280 black workers applied for work at Big Mart. 160 workers were hired by Big Mart. 820 were hired by Big Mart. There were a total of 980 applicants that want to work at Big Mart. The probability that a randomly picked applicant is white is equal to 700 white applicants divided by 980 applicants, which is equal to 0.7143. The probability that a randomly picked applicant is hired and is white is equal to 130 white applicants divided by 980 applicants, which is equal to 0.1327. The probability that a randomly picked applicant is hired, given he is white, is equal to the probability that a randomly picked applicant is hired and white, divided by the probability that a randomly picked applicant is white. White is behind the line. White is below the line, which is equal to 0.1327 divided by 0.7143, or 0.1858. Another way of computing the conditional probability is to divide the number of applicants that are white and hired by the number of white applicants, which is 130 divided by 7, or 0.158. The multiplication law provides a way to compute the probability of the intersection of two events, which is also referred to as the joint probability. It is derived algebraically by manipulating the conditional probability equation, which is the probability of A given B equals the probability of A and B divided by the probability of B. Multiplying both sides of this equation by the probability of B yields the following. So the probability of A and B is left on the right. So the multiplication law is the probability of A equals the probability of B times the probability of A given B. That is the conditional probability of A. That's the unconditional probability of B. Hence, the multiplication law multiplies the unconditional probability of B by the conditional probability of A. The probability that a randomly picked applicant is hired and white is 130 divided by 980, which is 0.1327. Using the multiplication law gives the same amount. The multiplication law is the product of the probability an applicant is white and the probability the applicant is hired given she is white. To compute the probability an applicant is white, we divide the number of white applicants, 700, by the number of applicants, 980. To compute the probability an applicant is hired given she is white, we divide the number of hired white applicants, 130, by the number of white applicants, 700. The product of these probabilities is 0.1327, the same thing. If the probability of event A is not changed by the existence of event B, we say that events A and B are independent. The statistical definition of independent events is two events A and B are independent if the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. If the two events are independent, the multiplication law changes. The multiplication law says the probability of A and B is equal to the probability of B times the probability of A given B. However, since A and B are independent, the probability of A given B equals the probability of A. So the multiplication law for independent events says the probability of A and B is equal to the probability of B times the probability of A, which was one of the very first things we talked about in this chapter. The hypothetical example below shows how many men and women at an economics research think tank were either promoted or not. There were 100 men and 20 women that were promoted, but 500 men and 100 women were not. 600 male economists work at the research think tank. 120 female economists work at the think tank. 120 economists are promoted. 600 were not. There are 720 economists at the firm. The probability that a randomly picked economist is promoted is equal to 120 promoted divided by 720 economists, which is 0.1667. The probability that a randomly picked economist is promoted, given the economist is a man, is equal to 100 male economists that were promoted divided by the 600 male economists at the firm, which is equal to 0.1667. Since these probabilities are equal, getting a promotion and being a male are independent events at this think tank. Recall our Big Mart hypothetical example. The probability that a randomly picked applicant is hired is equal to 160 hired by 980 applicants, which is equal to 0.1633. The probability that a randomly picked applicant is hired, given the applicant is black, is equal to 20 black applicants that were hired divided by the 280 black applicants, which is equal to 0.1071. Since these probabilities are not equal, getting hired and being black are not independent events. Bayes' theorem tells us about how the probability of something changes when we learn information. In the example that follows, we know from a drug lab's claim the probability of testing positive given the employee is a druggie. Since the company fires druggies, we would rather know the probability that an employee is a druggie given he or she tested positive for drug use. To compute the latter, we need additional information. For example, the false positive rate from the drug lab and prevalence of drug use among our employees. We want to ensure that our employees are not taking drugs because this is a safety risk. We contract with a lab to conduct drug tests because we have read that this lab's drug test is 94% accurate, which sounds impressive. However, while reading this, we also find out that there is a 5% chance of a false positive test. This means we might terminate the employment of somebody who we believe uses cocaine but really doesn't. But since this is so small and the accuracy rate is so large, we hire the company. Suppose our firm has 10,000 employees and that 1% of them are druggies. If an employee is found to be a druggie, we fire them for safety reasons. Let P denote a test that is positive. N denotes a test that is negative. D denotes an employee that is or who is a druggie. D superscript C denotes an employee who is not a druggie. Translating the information about the drug lab into statistical notation yields the following. From the drug lab, we know the probability a person tests positive for drugs given he is a druggie is 0.94. This is the lab's accuracy rate. The lab computes this by gathering up a bunch of urine samples from known druggies and uses its test to test for the presence of drugs in samples known to contain drugs. 94% of the time, the test indicates there are drugs in samples known to contain drugs. The probability a person tests negative for drugs, given he is a druggie, is 0.06. This means that 6% of the time, the test indicates there are no drugs in samples known to contain drugs. The probability a person tests positive for drugs, given he is not a druggie, is 0.05. This is the drug lab's false positive rate. The lab computes this by gathering up a bunch of urine samples taken from people who are not using drugs, who we know for sure are not using drugs, and we test for the presence of drugs in their urine samples. 5% of the time, the test indicates there are drugs in samples known not to contain drugs. The probability a person tests negative for drugs, given he is not a druggie, is 0.95. This means that 95% of the time, the test indicates there are no drugs in samples known not to contain drugs. We believe the following. 1% of our employees are druggies. Now, maybe we get this from the fact that it is widely reported in the region where our employees live, 1% of the people in the region are doing drugs. This is the prevalence rate of drug use by our employees. If 1% of our employees are druggies, then probably an employee is not a druggie is 0.99. Next, we illustrate the previous statistical information using a tree diagram. This yields the outcomes of this experiment. The first stage of the diagram shows the prevalence probabilities. On the top branch, we have the probability an employee is a druggie, which is equal to 0.01. The bottom branch, we have the probability an employee is not a druggie, which is equal to 0.99. In the next stage, we first graph the branches corresponding to the probabilities a person tests positive for drugs or tests negative for drugs, given the employee is a druggie, which is 0.94 and 0.06. Using the multiplication law yields the probability that an employee tested positive and is a druggie, which equals 0.01 times 0.94 or 0.0094. Remember the multiplication rule. The probability of A and B equals the probability of A given B times the probability of B. Using the multiplication law again yields the probability that an employee tested negative and is a druggie. Probability of A and B equals the probability of A given B times the probability of B. So according to the multiplication law, multiplying 0.01 and 0.06 is 0.0006. Going back to the second stage, we graph the branches corresponding to the probabilities a person tests positive for drugs or tests negative for drugs, given the employee is not a druggie, which are 0.05 and 0.95 respectively. Using the multiplication law, we multiply the probability of A given B times the probability of B to get the probability of A and B. In this case, the probability of testing positive and not being a druggie, which is equal to 0.0495, 0.99 times 0.05. Using the multiplication law again yields the probability that an employee tested negative for drugs and is not a druggie, which equals 0.99 times 0.95 or 0.9405. The probability of testing positive equals the sum of the probability of testing positive and being a druggie and the probability of testing positive and not being a druggie, which is 0.0589. The probability of testing negative equals the sum of the probability of testing negative and being a druggie and the probability of testing negative and not being a druggie, which is 0.9491. When you add them together, you get 1. To find the posterior probability that an employee is a druggie given he tested positive, we apply Bayes' theorem. Bayes' theorem is another way of computing a conditional probability. The expression in blue equals the prevalence of drug use at the company, namely the probability a worker at our firm is a druggie. The expression in red equals the probability of a worker at our company testing positive for drug use, given he is a druggie. This is a drug lab's accuracy claim. The expression here is the probability that a worker at our company does not do drugs. This expression is the probability of a worker at our company testing positive for drugs, given he is not a druggie. Question: what is the probability a worker is a druggie given he tested positive for cocaine use? This should be really high because the drug lab test is 95% accurate. To compute the probability, we must use Bayes' theorem. The probability a worker is a druggie is 0.01. The probability a worker at our company tested positive for drugs, given he is a druggie, is 0.94. The probability a worker is not a druggie is 0.99. The probability a worker at our company tested positive for drugs, given he is not a druggie, is 0.05. The probability a worker is a druggie and tested positive for drugs is 0.0094. The probability a worker is not a druggie and tested positive for drugs is 0.0495. The probability a worker is a druggie and tested positive for drug use is 0.0094. The probability a worker tested positive for drug use is 0.0589. The probability a worker is a druggie given he tested positive for cocaine use is 0.1596. This is much lower than one might have expected, given the drug lab's test is 95% accurate. This means that of all the workers that tested positive for drug use, only 16% are actually druggies. Question: what is the probability a worker is not a druggie given he tested positive for cocaine use? This should be really low because the drug lab's test is 95% accurate. To compute the probability, we must use Bayes' theorem. The probability a worker is not a druggie is 0.99. The probability of a worker at our company testing positive for drug use, given he is not a druggie, is 0.05. The probability a worker is a druggie is 0.01. The probability a worker tested positive for drug use, given he is a druggie, is 0.94. The probability a worker is not a druggie and tested positive for drug use is 0.0495. The probability a worker is a druggie and tested positive for drug use is 0.0094. The probability a worker is not a druggie and tested positive for drug use is 0.0495. The probability of a worker testing positive for drug use is 0.0589. The probability a worker is not a druggie, given he tested positive for cocaine use, is 0.8404. This is pretty high. And that means of all the workers that test positive for drug use, 84% aren't druggies.